talk. So basically, this particular lecture that we will be talking about here is more advanced topics. We will be covering some of the more advanced topics of gamma arrays. Now, if you will remember my last lecture where I talked to you about the importance of the coincidence matrix through various examples, right? Okay, now I'll be coming to that, but before that I'm just trying to summarize few topics here. You see on the slide here you can see the importance of gamma ray spectroscopy. Okay, you see it plays a very important role in the sense that through the various coincidences we can establish the decay scheme or level scheme of an nucleus. When a nucleus is formed in an excited state, many excited levels during the de-excitation they emit gamma rays, and they can also emit charged particles, thereby de-exciting to other nuclei. Now, using the coincidence conditions, for that we need detectors. Okay, now there can be various type of detectors. Gamma detectors, they will be registering the gamma coincidence. If we have gamma gamma detector, then gamma gamma coincidence will be there. If we have two or more charged particles detectors, then charged particle coincidence relation could be established, and so on and so forth. Similarly, using the angular distribution and correlation measurements, we can measure the multipolarity and spins. Okay, spins of the levels and multipolarity of the gamma transitions. And using a little bit more advanced detectors, I will talk to you about it in later lectures, we can measure the linear polarization. I intend to cover the topic of estimation of linear polarization for both orthogonal and non-orthogonal type of detectors. This will be very interesting. And through these observations we can measure the, you see, the parity of the level as well, right? Now another very interesting,
electron charge mass ratio.
no, this is electric or magnetic polarity. Okay, now you see another very interesting topic, and these are all will be covered in after the mid-sem exam is over, because these are all little bit advanced techniques, and that is the measurement of level lifetimes. And I will talk to you about the Doppler shift attenuation method and recoil distance techniques. Through this we can measure the level lifetimes. Now these are advanced topics. Now you see in the last lecture, if you remember, we talked about the various aspects. So we talked about the formation of an excited compound nucleus, then various decay possibilities we talked about, and then I talked to you how we can get information through the use of a detector array. Here I have shown just 6 detector arrays. Now you remember that we talked that there could be decay by 5 possibilities, say for example, and say if this particular nucleus X3, this has got say 5, no not 5, suppose this has got 10 cascades, different gamma cascades in a single nucleus, each emitting 10 gamma rays. Okay, so how many gamma rays will be emitted by this particular nucleus X3? It will be 10 into 10, approximately 100 gamma rays. Now suppose the same thing is true for all the other 5 nuclei. So what we will observe in the single spectrum, we will be observing 100 gamma rays from this one, 100, 100, 100 and 100. So in all there will be 500 gamma rays. Understand? This is a huge complex matter. Yes, Partho. Anyone?
বলছি ওই স্যার x3 থেকে স্যার 10 টাইমস 10 করে 100 কিভাবে গামারে ওইটা স্যার আবার বলুন, বুঝতে পারলাম না কিভাবে
Suppose you
100।
see this, I am shown here x3. Now this is a excited level of, there can be many excitations on x3. Now you see I have shown here some of the decay cascades, some rotational, some vibrational excited levels in x3 are populated as a result of this reaction. Now here you can see in this figure 5. Suppose there are 5 more. Now, interestingly, if these cascades, they are not connected to each other, then you can think of it that there are 10 total cascades of gamma rays, all belonging to the same nucleus X3. Now, this is a typical example of shape coexistence. You see, we can have various energies. These levels, you see, I have shown in the vertical screen, it is the energy axis. Now there are different excitations, but even at the same energy we can have vibrational as well as rotational level excitations as well during the collective excitation of the nucleus, right? So this is the reason why I am giving an example. So you see, if there are 10 decaying cascades from each of the nucleus, and each of the cascade, if they have 10 gamma rays, 10, 10, 10, 10, then from one nucleus, this X3, we will be having 100 gamma rays. And so from all these 5 nuclei decaying, we will have 500 gamma rays here. Okay, now suppose this axis, this is the energy, right? Suppose we know that we will be taking data up to 1 MeV. Why? Suppose it is so that all the decaying gamma rays, they are the gamma rays of interest from all these nuclei, they have energies below 1 MeV. So we do not need to take anything above 1 MeV. So we are going to take data up to 1 MeV only. Now you see, from this say 50 keV to 1 MeV, there will be 500 gamma rays. Okay, 500 gamma rays. And as I have talked to you in my last talk, they will be decaying nuclei and they will be also moving. As a result, their energy resolution will be a little bit worse compared to the scenario when they will be at rest. So if you assume that the energy resolution is around 3 keV, okay, approximate, then you can see that how many 3 keV bins will be there below 1 MeV. Whatever be it, you see, you understand? You understand? You see, if there are 500 gamma rays in this spectrum and we have energy bins of 3 keV, because 3 keV is the energy resolution limit. If two peaks arrive within 3 keV, we won't be able to resolve. Then this means that from 50 keV to say 1 MeV, there will be approximately 330 energy bins here. And how many gamma rays are there? 500 gamma rays. So this means there will be overlapping and a huge problem. Now this is because of single spectrum. Suppose we take coincidence spectrum, that is gamma gamma that I talked to you about, right? Then what will happen? We will have 333 into 333, so many energy bins, and as a result we will be now much better. We will be able to get this entire spectrum in a much better way. However, do note that we will see, as a result of the coincidence condition, once we put a gate on one of the gamma rays, the spectrum will become much cleaner. Okay, any questions? Okay, so now before I again proceed, so let me again recapitulate. So we are talking about the importance of coincidence spectrum and gamma rays. Do note, we have to remember, keep this in mind, that our ultimate aim by using this gamma array is to resolve all possible gamma ray decay sequences. Now, for this, we have to use sophisticated detectors, say for example, detector which has very good energy resolution. Not only that, it must have very good peak to total ratio. Otherwise, the weakly populated sequences of the cascades, the weakly populating gamma rays, দেখো এই যে ক্যাসকেড গুলো আছে এর low lying levels গুলো যে হয় gamma গুলো, they are strongly populated, but the higher ones, they are weakly populated. So if the detector, if it doesn't have number 1 good energy resolution, number 2 good peak to total ratio, number 3 good detection efficiency, full energy peak efficiency, if we don't have that, then the weakly population gamma rays, these ones, the higher ones, we will not be able to observe. Okay, that is, we will not be able to resolve. So keep this in mind, and for all this we must have very high granularity of the gamma array as well. Otherwise there will be 2 gamma transitions entering one detector, and as a result we will lose the effect, because of we will lose information due to summing. Right? Okay. So now let me ask you a very simple question. You see, now we are going again back to the basics. I want to give you a little bit flavor of some of the basic principles. You see, suppose epsilon is the singles photopeak efficiency of a gamma array. Then what would be the doubles photopeak efficiency? This is a sort of question. Now for that, let me take into account this fact that suppose we have got 3 detectors, 2 HPG detector and a suppressed HPG detector. Okay, which is a little bit better detector in this case. Now suppose each of these 2 HPG detectors, they have singles detection efficiency, full energy peak efficiency of 0.2, and this one has 0.5. Then the singles efficiency in this case will be, you see, if you do the overall, how much it comes out? It comes out to be 0.3. Okay, next, what about the doubles efficiency? This number comes out to be 0.08. Now do note that doubles is not equal to the single square. Now let me take a second example where all the 3 detectors are of the same type. Now if we do so, then you see in this case, you see, if we take the singles efficiency to be 0.2, then in this case the doubles efficiency will be equal to single square. This is a very simple observation. Okay, now so what we get from this very simple calculation is that if the array consists of same type of detectors, then the double efficiency will be equal to the single efficiency square. The same could be said about the triple efficiency, gamma gamma gamma. Okay, however, if the array consists of different type of detectors, then in that case the doubles efficiency will be lesser than that of singles efficiency. The same can be said about the triples scenario. Okay, any questions? Okay, so no questions, right? This is very basic. Now let me go to a little bit more complex case. So suppose the data is being taken in doubles coincidence mode. Okay, this is how we write double coincidence mode. M gamma is greater than or equal to 2. Then this data, remember, it will contain triples events as well, quadruple events as well. What do you mean by that? What do we mean? I will show you. what we mean is that there can be a data, one particular event when two gamma rays, one in D1, one in D3 are there. So this is a doubles event, right? Now there is a possibility that there could also be an event at the same time when one gamma is in D3, another is one in D2, another is in D3, and the third one is in D4. Then this is a triples event. Okay, 1, 2 and 3. Now when we are doing gamma gamma matrix, then this will contain information about both double coincidences and as well as triple, 4 and 5 coincidences as well. All the data will be here. I will show you a very nice example of this gamma gamma coincidence later on. So you see, even if we take data in doubles mode, there will be data of triples, quadruples and higher fold events as well. Okay, so if the singles photopeak efficiency is epsilon, then the fraction of events in which two gammas are detected is simply epsilon square. However, do note that the fraction of events in which three gammas are detected is 3c2 epsilon square into 1 minus epsilon. Now you must be scratching your heads. Why is this so? Now, before I give you an explanation, let me just tell you what happens in the case of 4 gammas. You see here, in this case, it will be 4c2 epsilon square into 1 minus epsilon square. You see, this factor basically means the detection efficiency for not detecting one particular gamma ray. So let me give you the reasoning behind it. Suppose 3 gammas are in coincidence. You see, a very simple cascade is shown here. Now, 3 gamma rays, namely gamma A, B and C. Okay. Now, if A and B are detected but C is undetected, you see, A and B are detected but C is undetected, then what will happen? Then the fraction of such events will be A, okay, efficiency of A, detection efficiency of B detection multiplied by the detection efficiency of not detecting C. So it will be 1 minus epsilon. Similarly, if A and C are detected but B is not, then we get a similar thing, but the ordering will be different. This was A, B, C. This is A, B, C. And same for the case if B and C are detected, and then A will not be detected. So the total number of such events will be proportional to, you see, 3c2, or basically 3 into epsilon square 1 minus epsilon. Okay. Now same thing can be said in case of 4 gamma rays. We can do this sort of multiplication. This I just represented a symbolic thing, and you can see here we have 6 terms or 4c2. This is the reason behind writing so. Okay, you understand? Any questions? Rajiv?
Yes, sir.
Or anyone? Okay. So this is a basic consideration. Keep this in mind that even if we are taking the doubles data, there will be cases here where higher fold events will be present in our data. So let me talk to you about a separate thing. Suppose if epsilon is the probability of gamma array for detecting single photon, then the fraction of events in which 4 gammas are detected appearing in the quadruples, triples, doubles and singles gamma gated spectrum. This is the reverse case of the previous one. Then you will see in this case the probabilities will be like this, here like this, while epsilon is the singles photopeak probability of the array. Okay, now this is just a different case compared to the one which I have discussed to you now. So what we did today, we talked about this overall summary. Then I discussed to you about this 500 gamma rays here, and since we have 3 keV bins, so 500 gamma rays within the 1 MeV zone, there will be, if each energy bin is of 3 keV, then there will be total 330 bins or so, and within this 330 bins, if 500 gamma rays are there, then some of the gamma rays Of course, there will be overlapping in case of single spectrum, but if you take a coincidence, then there will be 330 into 330 energy bins, and we will have more space for them, right? And so after that, I gave you a very simple example of how the singles and doubles efficiency of array. Through an example, I showed you what does it mean to have, how to calculate, how to estimate. So this was the second thing we talked. The third one is this thing. That means, suppose the data is being taken in doubles mode, then what fraction of events of higher folds will be there? We talked the logic behind it, and lastly we talked about this case. Okay, so no questions till now? Okay, so let me talk about the last topic today, which is the concept of resolving power. Basically, we can have different type of arrays. Now what we want to do is we want to know how good our array is, or basically we want to have a figure of merit of our array, or you can say how good our array is in its ability to observe the weak branches. That means the gamma rays from the levels which are very less cross section, weakly populated levels. Okay, so you see, we want to basically benchmark our gamma ray spectrometer, right? So let me start with this very basic case. Suppose we have this nucleus. Suppose some nucleus is there which is excited during the reaction, and this is one of the bands of interest, and this band of interest has intensity, suppose alpha. And how many gamma rays can you see in this band? This band connects to the ground state of this level through the transition E1, and we have the higher ones E2, E3 and E4. And other than this, we do have other bands from the same nucleus, right? They will be there. I'm just denoting them by red because we are not interested in it. We want to particularly study this band. This is how we do gamma ray spectroscopy. We are mostly interested. Suppose this E1 and E2 are known for a particular band in a nucleus. We want to do the spectroscopy, and we want to extend the level scheme to higher levels and see. And then we would like to study the structure of these states which we were unable to study before because they have very low production cross sections, and the weakly populated, because of their weak population, the de-exciting gamma rays we could not observe before. But suppose now we are able to observe this E3 and E4 transition, so we have to capture them effectively so that they have good statistics, and then from their study we will be able to get information about these two levels. So I have given you a very simple idea about how we do the level scheme spectroscopy. Basically our aim is to add the level schemes and thereby study the various structures of the nucleus. Okay, now so basically we want to carve out the tiny intensities alpha. Here I have given you a very simple example. You see, this is the single spectrum. All measured gamma rays are here. You see, this is so very complicated. Now this is twofold coincidence. Twofold coincidence means gamma-gamma coincidence along with one energy gate. This is threefold coincidence. That means we have put gate on one gamma, another gamma, and observing the third spectrum. This is much cleaner. Do also note if you can. আচ্ছা আমি এটা রেকর্ড করছি, এটা তোমরা পরে এই জিনিসগুলোই আমি বলছি এখানে। ওকে, আচ্ছা এবার যেটা যেটা ইম্পর্টেন্ট সেটা দেখো হচ্ছে, ইউ সি if you observe these axes closely, then you will see these are huge counts. There is a multiplication factor here, counts into some factor of 10. These are huge counts. But if we go on higher coincidences, you see the counts drop. Okay, counts drop. Obviously we are able to get sharper peaks, we are able to get more information, but remember, the result of taking higher fold coincidences is a very strong drop in the statistics. So we are here measuring higher fold coincidences and applying the F-1 gates on energies. This is, I've just shown you an example. Obviously, we do know that energy resolution, that means narrower gates. If we have better energy resolution, we can make narrower gates. And efficiency helps more. How? In the higher fold or higher fold coincidence gated spectra, if the detector efficiency is very high, then we will be having sufficient statistics. We will be having very good statistics there. Now, you might ask yourself, so how important is resolution compared to efficiency? Or there may be something else which is important here. And why does the gating improve the peak to background? What do you mean by peak to background? You see, here, what is the background level? This is the background level here. This is the background level here. This is the background level. You see, each time we do the fold, the background is also decreasing. The peak counts are decreasing, the background is decreasing. But what is important is signal to noise ratio. Remember, signal to noise ratio. Now here, the signal is the full energy peak and noise is the background. So we must have a scenario, we must have that in each of these higher fold events, in each case, we have better peak to background ratio. This you can obviously see from here. Compared to the background level, this is peak, this is background, this is peak, this is background. You see there is an improvement here. Background is very much lower and the ratio is much better here. So the question is, why does, as we keep on doing higher fold coincidences, or if we keep on doing the energy gates, then this gating improves the peak to background ratio. Okay, so here we have an example. You see, first let us try to understand this plot. So we have this level structure. Remember, this is what we were studying, this one. Okay, so we have this level structure, E1, E2, E3, E4. They are all coincident with each other. Now let me see this axis. So this is the typical gamma matrix. Okay, you can see. Now with energy E1, which other gamma rays are in coincidence? E2, E3 and E4. So if we observe E1, then if we put a gate on E1, then we will observe E2 here, E3 here and E4 here. So with E1, we will observe E2, E3, E4 coincidences. Similarly, let me observe E2. So which gammas are in coincidence with E2? They are E1, E3 and E4. Similarly, here you see with E2, the gammas in coincidences are E1, this is E3 and this is E4. Similarly, the other plots look like this. Now here, these blue dots, they belong to the peak, and the red one are the everything else, including the Compton background. You remember this idea? The peaks of interest, they correspond to this blue color, and the everything else, they belong to the reddish color. Okay, now what is delta E here? This delta E is basically the effective resolution, and this is the result of both the intrinsic detector resolution and the result of the Doppler broadening. Remember, we talked about it previously. Now, what is AC? AC is the average energy separation. Average energy separation between the various transitions. So, energy separation between what is E2 minus E3, what is E3 minus E2, what is E4 minus E3. We make the differences and make them average. That is the sort of average energy separation. Okay. So average energy separation is E4 minus E3 plus E3 minus E2 plus E2 minus E1 divided by 3 for this case. Okay. Now, you see the EX EY coincidences go into peak here, the blue, just as we have mentioned here, and everything else is spread over the reddish area. Since they are not coincidences with any of these gamma প্রচুর কাজে লাগে। যেরকম অপটিক্সে আমাদের রিজলভিং পাওয়ার আছে, ওই রকম নিউক্লিয়ার ফিজিক্সেও আমাদের এই জিনিসগুলো এখানে কাজে লাগে। ওকে, নাও আমি কিছু আর বেশিক্ষণ নেই, কিছুক্ষণ আছে। আচ্ছা, সো okay, so now we will make coincidence. Suppose if we do a projection, right? That means if we observe in this 2 by 2 matrix, if we observe everything along one particular axis, then what will we see here? These 3 peaks will be added. 1, 2, 3. We will get here. These 3 peaks will be added here. These 3 will be here, and these 3 will be here, and the background will be here. So let us do the analysis of everything with respect to the projection. Everything along this axis. So we have got this. Now if so, this projection corresponds to all measured gamma rays, right? Now what do we observe? If we do an energy gate around the AC only, this AC, what will we observe? We observe just these 3 gamma rays. So these 3 transitions, that means E1, E3 and E4, right? E1, E3, E4. However, do note that previously we were in this projection we have 1 2 3 1 2 3 1 2 3 1 2 3. If this is the peak, then this time compared to the 3 dots we have got only 1 dot. So the statistics of the peak is 1/3. However, do note that the background statistics has also reduced similarly to 1/3 of that previous case. Now this is an approximate number. Okay, however, if we do a cut along this delta E here, this one, energy resolution, if we do a cut along just the peaks, then something even more dramatic happens. What is that? That is, the peak statistics remain the same. However, do note this, we are getting rid of this part of the background, and this is reflected over here. So compared to the previous case where the background level was very high, here we have an improvement of the background by a factor of delta E by AC, delta E by AC. So because we are losing this part of the background. So we have a huge improvement of the peak to background factor, by a factor of AC by delta E, right? Now, okay, so but we have to pay. And what is that? You see, interesting, this is the gamma spectrum. Now suppose this is a peak,
Sir?
right? And we in this gamma spectrum,
বলছি স্ক্রিনটা দেখা যাচ্ছে না তো।
peak into Compton, peak. So you see this example, basically peak to total means the probability to count a detected gamma in the photo peak or full energy peak and not in the Compton plateau. Okay, now let us take an example. If the peak to total is 0.2 and we have got 2 gamma rays, then the probability of detecting both of them in the full energy peak is 0.2 into 0.2, which is 0.04 or 4%. The probability of detecting one gamma in full energy peak along with one Compton, these are the cases shown here. You see, this is peak into peak, and then this is peak into Compton. These are the scenarios. It is 16%, and do note that the greatest one is the probability of detecting both gamma rays in Compton. 64%. Okay. Thus, we lose the peak to total in peak intensity each time we increase the fold factor. This is important. Now, regarding that, however, there is a reduction in the background factor. And how it is that? Through the last example, pictorial example, we observe that each time we increase our fold F, we improve the peak to background ratio by this factor. Okay, where did we observe? We observed this thing here, right? Compared to this case, we went to this one, and then when we went to this case, we observed this reduction factor. And this is called the background reduction factor R, which is defined as this. Now, the origin of this 0.76 is that delta E is the FWHM of the peak, and you can find it out for statistics, assuming that 76 has the 76% of the peak intensity. Like for peak to total ratio, we reduce the peak intensity by factor 0.76 with each cut window of width delta E. So what we observe is that a very good value of peak to total ratio is as important as a small value of delta E. So very good value of peak to total ratio and a very small value of delta E, they are both required to have a very good reduction in background. Note that if we can't do the reduction in background, our data peak to background we will not be able to get a good data out. Okay. Now, for fold F is equal to 1, the peak to background ratio for a branch with intensity alpha is alpha R. Here, note that the backgrounds means the background under the peak. Now, if we go to a higher fold F, then the peak to background ratio changes to alpha into R to the power F. F is the fold. 2-fold F is equal to 2, 3-fold F is equal to 3, and so on. If N0 is the total number of events, then the amount of detected counts, capital N, in the peak is this number, that is equal to alpha N0 into epsilon to the power F, where epsilon is the full energy peak efficiency of the spectrometer. For a minimum intensity alpha 0 to be resolved, this will be possible if alpha 0 into RF equal to 1. And suppose we take the number of detectors to be capital N. Also, number of detected counts in the peak. No, not that number of detectors is not here right now. Suppose if we have that, then root n is of the order of 10 and we will be able to resolve the spectrum. Then we define the resolving power as RP for resolving power, as 1 by alpha 0. And if we take the three things together, then we get this expression of Rp equal to exponential log of N0 by N divided by this term. So this is the figure of merit for the array which we wanted to find out. You see this plot? Okay. Now, as alpha is equal to 1 by Rf in the previous case we found, right here, alpha is equal to 1 by Rf, we can reach any small alpha by making F large enough here, that is measure sufficient high fold coincidences. This thing here, if we do this plot, fold versus alpha, F versus alpha, we have good. And this is, we have this part, we have the insufficient peak to background compared in this plot here. On the other hand, we have to measure f-fold coincidences, this one here. We have to measure reality,
পিডিএফটা ভালো
this
করে
in
দেখে
constraints, right? So I will stop up to this part today.
স্যার মেডিকেল
I'll
নিউক্লিয়ার
send
ফিজিক্সটা
you
যেটা ওই
the
আজকে যেটা পড়াচ্ছিলেন
slides
সকালের
video
দিকে, ওইটা কি
as well.
সিলেবাস শেষ
Do
ওটার?
look into
মানে
it,
মেডিকেল ফিজিক্স যতটুকু?
and if you have queries, I think you will have, then we can discuss in the next class. Any questions?
বলুন স্যার।
স্যার পিডিএফটা ভালো করে দেখে নিয়ে বলুন
হ্যাঁ ঠিক আছে, okay. I will give this to you, okay?
স্যার মেডিকেল নিউক্লিয়ার ফিজিক্সটা যেটা ওই আজকে যেটা পড়াচ্ছিলেন সকালের দিকে, ওইটা কি সিলেবাস শেষ ওটার? মানে মেডিকেল ফিজিক্স
না, ওটা আরো পরে হবে, কমপ্লিট হয়নি, আমি জাস্ট তোমাদেরকে বোঝানোর জন্য আর কি বলছিলাম এই জায়গাটা। এবার দেখো এইটা যেটা বলছি এইখানে দেখো ইন্টারেস্টিংলি দুটো জাস্ট দেখাই যে এত পড়াশুনো কেন, কি প্রয়োজন আছে। ইউ সি দিস প্লট শোজ দ্য এভলিউশন অফ গ্যামা রে স্পেকট্রোস্কোপিজ রিজলভিং পাওয়ার। This is the resolving power. You see the number 1, 100, 10,000, 10 to the power 6, 10 to the power 8. And this is possible because of the development of newer and newer detectors as well as techniques, which has led to the possibility of detecting gamma rays from the levels which have very low cross sections. You see, another thing এখানে দেখো, this is the 156 dysprosium, first observed, you see, in 1963 using just sodium iodide detector, the one that we have in the lab. You see, this was in 1963, we just observed this, and later on with the help of better and better detectors, you see, this is what we have. This is 1998 data. This is the very high fold data. You see this peak to background, there is hardly any background, there are just peaks over there. So you see, this is the power of the detector array, and there are other effects also shown.